All right, ladies and gentlemen, good morning or afternoon. This is Mr. Ackerman, your disembodied teacher, coming to you live from yesterday evening. There you go, there's words. I apologize for being out. A new year, new month, new illness. It seems to be almost at the beginning of every month my child gets sick. It's exciting. It's not fun at all, but that's okay. We can move forward, we can power through this. We have new material, and with the advent of technology, we can teach this. Feel free to send questions via Schoology as you look at some of this stuff. I will gladly, especially if it pops up, I can help you out, or at least think about conversation points tomorrow. Goal is to be back tomorrow. Shouldn't be any later than that. That's what I'm hoping. The topic we're going to deal with, typically this is taught actually before the last thing we dealt with rotations. Rotations are kind of weird and strange, but what I like about rotations is conceptually, there's not a lot of weirdness to it, and I'm going to talk about what I mean by weirdness in just a minute. The shapes, while they come out as strange, what we're going to talk about next can actually make some even stranger shapes. So, when I talk about volumes by rotation, one of the things we did is we talked about taking these shapes and kind of thinking about, what the orientation of the shape is. So like this particular problem, if we would have drawn it in the questions below, we talked about these being dy disks, and we knew they were because we imagined how the disk was laying. So like this particular question, we would have had, some sort of dx disk. So I don't know, maybe it looks kind of like this. You got your little hole somewhere in the middle, something like that, with a height that would be some sort of dx, and we're always trying to label what that d something is on this. But the cool thing about a disk is the disk is always a circle, every single time. And if we really think about this problem, all this problem is saying is that when we look at the formulas for the area of or volume of a rotation, what we say is that we just take the area of a circle formula times dx and integrate that over a to b, and we say, hey, look, now it's a volume and we're good. So we're essentially taking the area of a circle that is a consistent piece. We would call this a cross-section. Now, the weird part is in this one we're creating the cross-section by doing an action, but we're essentially just taking a cross-section of this and saying, if I grab a piece and pull a piece out all the way across, it makes a perfect disk. Now, we're going to ask ourselves, what if we didn't spin it, but what if I just told you that perpendicular to an x or a y axis, what if I just told you a specific cross-sectional shape? How many different 3D figures can we make? How many strange 3D figures can we make? How weird can we get with this? And that is what we're going to look at today with cross-sections that we're familiar with, such as squares, rectangles, triangles, and semicircles. So when we go through and we deal with this, what we want to look at is we want to kind of look at this particular problem. And hold on, I got to find out where I put my thing. This first thing we're going to look at is going to be a volume, and we're going to have a volume with a cross-section perpendicular to a fixed diameter of circles, circular base that's a square. And we're going to be perpendicular to the x-axis in this particular case. So this is a circle. It's got a fixed radius of 2. We've got a set up diameter, and what we're going to do is we're going to look at some chords across the x-axis. I want to note that all these chords are perpendicular to the x-axis. So if that's the case, I got these perpendicular to the x-axis. What we're going to do is we're going to create squares. And now, so notice that doesn't do anything, but if I drop this, whoa, craziness, I love it. We can see that what we're saying is that along each one of those chords, we're going to lay down a square. And what do we know about squares? Square sides are all the same length. So when I rotate this back up, and I'd love to be able to just stop it, there you go. When we look at this, all of these random chords that are perpendicular to the x-axis, obviously along the edge furthest from the center over here, those are going to be really short squares because that chord would be very tiny, but once we get to the center, that'll be the largest, so it's going to be this interesting thing. And what we're going to say is that there's this cool three-dimensional shape that we're going to make. And what we're going to do is we're going to take this square and we're going to sweep this square all the way across. We're going to have an infinite number of squares that go from the -2 all the way out to the 2, and you can see that it starts very small and gets bigger. Well, what would that shape look like? Let's find out. See, what we can start doing is now our solids that we're dealing with, now we're not just saying, hey, this is a cube, hey, this is a sphere, hey, this is a cone. Now what we're saying is we're saying, man, what do we got? We got some really weird, creepy looking Pringles can thing here. Honestly, it kind of looks like a soccer stadium to me a little bit. I could see a soccer stadium totally being designed like this, where you got the two sides that kind of come down to a point. You know, the overarch might be a little bit of an extreme thing. Maybe that's what they're going to use to like block out sun or something. But you can do some really cool stuff with this messed up Pringle thing. And of course I can put those 4 squares back in and you can see those squares are just along the chords, and each of those squares would represent a specific area of one of each one of those chords, except it wouldn't just be the 5, it would be an infinite number of them. Whoa. My question to you is, what's the volume? How do we find a volume for a question that difficult and that complicated? And what we have to recognize is really all we're doing is taking a bunch of areas. If I take those 5 squares, if I take all of these squares as these are getting made, if I take the area of all these squares and add up all the areas of all the squares across the x-axis from -2 to 2, then just like the paper example that I showed you yesterday, where one sheet of paper really seems like just an area, but 20 sheets of paper suddenly looks like something with a volume, just like that, we can do the same thing with volume, or with these. So what we do, and it's actually very simple. If I have a cross-section of area A of x, taken perpendicular to the x-axis, so they're going to tell me what I'm perpendicular to. All I do is I simply integrate my function from some a to b of whatever on earth the area function is. This is just the area function. So this might be length times width. This might be the side length squared. This might be a radius divided by 2. This might pi times a radius divided by 2 as a semicircle. 1/2 the base times the height if they're triangles. If I want to do this same thing with respect to perpendicular to the y-axis, I simply integrate along the dy. Now, things get all sorts of wacky with this, so I want to talk about some of the things I do with this, with these types of problems. So the first thing we're going to do is we're going to set up integrals needed to find the volumes for the solid whose bases are bound by the area of the graph, whose cross-section of this. I want to point out this is just set up the integrals. This isn't solve, this isn't calculate. These questions get really hard really fast, and I don't want to deal with a really hard really fast right now. I just want to answer questions. So let's draw our base. First thing I want to do is I want to figure out where on earth is my base. So I may set these two functions equal to each other just to make sure I know what on earth I'm doing. So what do we got? X plus 3, x minus 1. So we know that these two functions intersect at x is equal to -3 and +1. So when x is -3, we know our y value is 9. And when x is, jeebus, 1, we are, yeah, okay, well, that's terrible, but we're going to go with it. 9, or we're going to go to the point 1, 1. And what do I have? I've got two functions. I've got y is equal to x squared. It does something like that. And y is equal to -2x plus 3. Yeah, it wasn't too bad. Now, one thing I'm not going to do is I'm not going to shade. The shading I'm actually going to lead to the next piece here. So we've got a region. Nothing new here algebraically, the same exact stuff we've been doing for a while. These are perpendicular to the x-axis. So because I'm doing something that has a specific direction, when I go to shade this, what I'm going to do is I'm going to shade this in such a way that I can see, hey, these are perpendicular to the x-axis. So looking at this region, but I want each of these to be set up perpendicular to the x-axis. So you can imagine on each one of those lines, what I'm going to do is I'm going to drop these different shapes on it. Now I would try to draw this, but I am so artistically incapable it's not even funny. So let's start with this first thing, a rectangle of height 4. So the first thing I want to do, after I've drawn my picture, I've identified all of this, I'm looking at rectangles of height 4, I want to know what is the area function for this? Well, an area for the rectangle of height 4 is just, area of a rectangle is just base times height, and they tell me that the height is 4, so this is just 4 times the base. So I've got to figure out how long is the base going to be. And the base is going to be that distance from some point above to some point below. So in this case, it depends on where on the x-axis I am, because if I'm close to this side, it's not very big at all. But as I get towards the center, it gets larger and then shrinks. And that's going to be determined by how far apart the linear negative 2x plus 3 is from the quadratic x squared. So I just got to write a function that works for that. This is going to be the upper function, negative 2x plus 3, minus the lower function, x squared. So I can restate that the area of my shape is going to be 4 times negative 2x plus 3 minus x squared. And I can distribute that. That's fine if I really feel the strange desire to do so. Now that doesn't do anything. That just tells me the area given any of the rectangles. Now what I need to do is I need to add up my rectangles. So I integrate from negative 3 to 1 of my area function I just found. 4 times negative 2x plus 3 minus x squared. And what am I saying? I'm saying that here is my base, or here is my height of 4, times my base, depending on where along the x I am. And I'm going to add together all of those across from negative 3 to 1. And this dx is a third dimension. And suddenly we don't have just areas, we have a volume. We could solve this. This wouldn't be too hard of a question to solve. The more interesting of the two is the semicircle problem, so let's take a look at that. Semicircles, we know that this has an area that is equal to 1/2 of pi r squared, and we've got to figure out what on earth r is. We know 1/2, we know pi, but what is the r going to equal? So r is a radius, and what we have to catch here is that the distance from the red to the blue would be the entire distance across the entire semicircle. Do I have an example of one of these? Oh, it's still sweeping. Go away. Semicircles. There it is. So if I show the segments here, this is perpendicular to the y-axis. But if we show those semicircles, each one of those chords is not a radius. Each one of those chords is a diameter across. So if we wanted to kind of see what that solid looked like, which is really kind of a cool little weird wall mount thing. But you can see that each one of those semicircles, that distance between, let me rotate that back, that distance across is just is going to be the diameter. So those chords don't represent radius, they represent diameter. I have to do the negative 2x plus 3 minus x squared, and I actually have to divide that by 2. That's a radius. Half the diameter is a radius. So that means that my area function is 1/2 pi times negative 2x plus 3 minus x squared over 2, or I could write that as 1/4 pi negative 2x plus 3 minus x squared. So if that's my area function, then my volume is the integral from negative 3 to 1 of that particular equation, 1/4 pi times negative 2x plus 3 minus x squared dx. Done. Now the only thing I will point out, I may rewrite this slightly. I might call this 1/4 pi times the integral from -3 to 1 of 2x plus 3 minus x squared dx. I might call it that because I like to factor out the constant. So here I may choose to factor the 4 out, but I won't try to factor anything else. So in a sense, this is kind of like optimization related rate stuff, where not as bad as optimization and related rates, but really all I have to do is know the equation I'm looking for, identify which direction the chords go, and everything's set up for me. In this example right here, we can see that we've got some shape. Okay, area bounded by the circle x squared plus y squared equals 9. So what do we have? We have a circle with a radius of 3. I've done better. 3, -3, 3, -3. And I tell you in this problem that we have cross sections perpendicular to the x-axis. That's important. So I'm going to draw my perpendicular cross sections across the x-axis. So I'm taking this shape. And I am going to try to find this volume. And I tell you that these are equilateral triangles. And even better, I don't expect you to know the equilateral triangle formula. I am going to ask you that multiple times on your homework. Look back at your notes. But I tell you what the area of the equilateral triangle is. Each one of those is going to be s squared times the square root of 3 over 4. Which means all you've got to do is figure out what on earth is s. Now this is a little bit trickier s because, whoa, we got to turn this into a y equals equation. So first off, let's solve that because I can't do this until we look at that. So this is y is equal to the plus and minus square root of 9 minus x squared. Be careful, the plus and minus is going to be important because I want to deal with that above and below. So I would say, well, what is s? S could be the positive square root of 9 minus x squared minus the negative square root of 9 minus x squared. Or, and I could combine those, or I could realize using symmetry that all I really have to do is check out 9 minus x squared, the square root of 9 minus x squared, and that distance is going to be the same distance above and below the x-axis, so I simply double it. Now, symmetry or hand calculating out the two equations, I don't care which one you do, although I will tell you that symmetry is going to make your life so much easier in just a couple of weeks. When we get to polar graphing, you are going to love the symmetry concept. So if I want to find the volume of this, I can go from -3 to 3 of the square root of 3 over 4 times 2 times the square root of 9 minus x squared dx. Or again, I would simplify this out and call this the square root of 3 over 2. I would eliminate these, factor this out, and call it this. But remember that symmetry thing I just talked about? That's a really gross integral. We actually can't solve that integral as it stands. But what I can do is I can realize one of the things that's really cool, and if this confuses you, you can put it aside. You've probably learned with the integrals that you really hate the ones where one of the numbers is not a 0. 0 is one of the most beautiful numbers ever. Multiply, plug in a 0, it becomes 0. Multiply by 0, it becomes 0. We like 0 a lot. And it would be nice if we could just have a 0. So what I can do is I can recognize that if I go from 0 to 3 and double the whole thing, I would get the same answer. So if I multiply this by 2, I'll get the same exact answer, which gets rid of some of the nasty numbers. That's going to factor this out and call this the square root of 3 times the integral from 0 to 3 of the square root of 9 minus x squared. And in some questions, we'll use symmetry. In some questions, we won't. If you use it in a free response, you get credit. If you don't use it in a free response, you get credit. So just be aware that that exists and that symmetry, I like the word symmetry, is your friend. I hope I spelled friend right, and if I didn't, don't laugh at me. All right. Last problem I want to work through, and then we're done for the day, folks. And then you can work on some problems as you need to. So we've got a base of a solid. It's bounded by y is equal to x squared. Y is equal to 0. I'm going to graph y is equal to 0. That's a nice, easy, pretty graph. All right. So that's the x-axis. That's y equals 0. We've got x is equal to 2. I like that graph. Here's x equals 2. Here's y equals 0. And, oh, shoot, we're going to use brown. And we've got y is equal to x squared. Right there. This is x squared. For the solid, each cross-section is perpendicular to the y-axis. Oh. So now we've got to draw our cross-section, our little lines here are cross-sectional pieces, and they're going to be perpendicular to the y-axis. That means this is going to be a dy problem. I need to go from wherever here is up to here. So what the heck is this? This is the point 2,4 where these two intersected, right? So that's going to be important. So let's deal with a square. Area of a square. Area of a square is simply the side length squared, so we need to figure out what on earth is a side length. So in this problem, we take a look, we work on this a little bit, we start kind of mapping this out. We realize really quick that because this is going to be a dy problem, okay, if we imagine these are these squares that we're pulling out, we're going to pull them out and they're going to be laid sideways, just kind of like the same problems we had with the discs. So we have these weird squares, or these weird like squares with a, remember, a super thin piece that we're going to call a dy piece, that we're going to have to travel this from 0 to 4. Well, the problem with that is that these equations don't work very well. What's defining this? I need to turn this into x is equal to the square root. I need to turn this function into x is equal to, oh, I'm writing down an equation. I'm not telling you where it came from. I'm going to turn y is equal to x squared into x is equal to the square root of y. Now you'll notice here I didn't do the plus and minus. I don't need to deal with both sides of the quadratic, so I'm okay with this. So if I think about that, I got to figure out how long each one of these is. So that's going to be the greater, the largest minus the smallest, or in this case 2 minus the square root of y. So our area is going to equal 2 minus root y squared. So my integral, we know, is going to be between 0 and 4 because those are the y values that depict this. Our area function is 2 minus the square root of y squared. We say dy. We smile, we nod, and we go on our merry way. Ladies and gentlemen, I know that that was a lot. So what I plan on doing is giving you an opportunity. You've had about 25 minutes of video, plus 5 minutes to kind of get yourself started. So I'm going to give you the opportunity to work on this today with each other. I have an answer key that's already up for both rotations as well as for cross sections. Have questions ready for me tomorrow, and if we don't have questions, then we will just proceed into the next piece of information, and we will go from there. I hope you have a fantastic day, and I really do look forward to seeing you tomorrow.